So when we look at what we got 1, 2, 3 NADH, which is a temporary energy molecule. We got 1, 2 carbon dioxides. We got 1 ATP, and we got 1 FADH2. But, like I said, it happens twice. So we multiply this whole thing out by 2. And what we really actually have are 6 NADH, 4 CO2, 2 ATP, and 2 FADH2s are what's coming out of the Krebs cycle. So far, glycolysis has given us 2 ATP and 2 NADH, that temporary energy. Transition stage has given us 2 more temporary energy NADHs. And Krebs now has given us 2 ATP, 2 FADH2s, and 6 NADHs. So far, we've got 2, 4 ATP, 2 FADH2s, and 2, 4, 10 NADHs. Right? So we move on now to the electron transport chain. But the problem is that we didn't really end with anything in Krebs, because Krebs just goes round and round and round and round. There's no molecule that ultimately comes out. So something else has got to be going into our electron transport chain. In our electron transport chain, the idea is that we're now going to take all of that temporary energy. So now, temporary energy, which we're talking about NADH and FADH2, is going to get turned into ATP, because that's the whole goal of cellular respiration. We're trying to make ATP. Electron transport chain is going to help us do that. The NADH and the FADH2 are going to carry electrons into the electron transport chain. Those electrons are going to carry that energy that we're looking for. For every 1 NADH, we can make 3 ATP. For every 1 FADH2, we can make 2 ATP. So remember, we asked which one gives us more bang for our buck? NADH. NADH is going to generate better energy. But FADH2, close second. So, at the end of the electron transport chain, oxygen is going to come into play. So here's where our oxygen really gets used. Right? The oxygen is going to take the hydrogens to make water. So basically, all right, an easy way to think about our electron transport chain is that NADH versus FADH2 are ultimately each going to be converted into ATP. 3 versus 2. What's going to happen is that FAD and NAD are going to leave their hydrogens. They're going to become uncharged. And in the process of becoming uncharged, we've got oxygen that we breathe in. That oxygen that we breathe in is going to come in and pick up those hydrogens to make water. Now remember, in photosynthesis, the water split in stage 1 to make oxygen. So isn't it kind of appropriate that now the oxygen comes back in, picks up those hydrogens, and turns back into water? Right? So at no point does oxygen become carbon dioxide or carbon dioxide become oxygen. Right? It's all about the water and the oxygen being transferred back and forth. Now, so we've got water coming out, oxygen going in, and we've got NADH and FADH2 going in versus ATP coming out. But remember, we didn't have just one NADH. What we actually had were 10 of them. And FADH2s, we had 2 of them. Because if we go back and look at what we had gotten so far, what we had so far was that we had 10 NADH and 2 FADH2s. So, 10 NADH, 2 FADH2s, which means really, this is times 2, oops, this is times 10. So we get 30 ATP out of the NADH, and we get 4 ATP out of the FADH2s, which gives us a grand total of 34 ATP coming from the electron transport chain. So if we really want to stop and look at our math, we've got 30 ATP from the NADH, 4 ATP from the FADH2s, which gives us 34 grand total. Animation there for you guys to watch. And if we look at aerobic respiration as a whole, there's 34 ATP coming out of the ETC, 2 coming from the Krebs cycle, and 2 coming from glycolysis. So we get 38 ATP total. Look at where the majority of it comes into play. The majority of it is coming in the electron transport chain. Majority of energy made, electron transport chain. That should wrap it up for aerobic cellular respiration. The next thing we'll worry about is anaerobic cellular respiration.